fact that you can talk to people who have had some impact on your career, kind of listening to how they think, how down to earth they are, is just, great.
Hello, everyone. Welcome to my talk about C++ parallel programming models. A little bit about myself. In my day job, I'm a database internals developer in a startup called Regatta Data. We're building a database, a distributed database that can handle both low latency transactional processing, OLTP, and large-scale analytic processing, OLAP, and we're doing it using C++, and we work on the full stack from the lowest level storage up to distributed transaction management and everything in between, parallel data processing, and so on. So in general, if you're looking for a very interesting field with interesting problems that can be solved using C++, I highly recommend data processing. Besides my day job, I'm involved in a local C++ community. This is my first CppCon, but I'm a co-organizer of the Core C++ conference, which will take place for the 6th time next month in Tel Aviv, Israel. Besides that, I'm a co-organizer of a local meetup called Haifa C++, located in Haifa in the northern part of Israel. And during COVID, since I'm not a big fan of online events and I was missing the community activity, I opened a WhatsApp group called Talking C++, which has been active since with over 500 people. This is like another dimension of community activity, which I also highly recommend if you're looking into this kind of community. It's fairly active, mostly about C++, but not only, and it's nice to have this kind of aspect. So, to the point, why do we care about parallel programming? So, the obvious reason is performance. We have multi-core hardware, and we want to be able to use it to the full. Another reason is to be able to hide I/O latency. If we send some I/O work, then we want to be able to do additional processing while that I/O is taking place. And to a lesser extent, we might want to be our application, if it's user-facing, we might want it to be more responsive. Why is it hard? Well, parallel programming is notoriously non-deterministic. It involves data races and deadlocks and so on. And having some kind of structure really helps in dealing with those issues. So a programming model provides us some structure for our program or our algorithm. And this allows useful abstractions. This means that the user can better understand what's happening in the program and reason about its correctness. And on the other hand, it can allow the library or framework to provide useful features and abstraction that help the user. And at runtime, we can have a runtime that operates according to a certain structure, and it can optimize scheduling and so on. So both of these aspects, the way you code and the way the program is executed, are crucial in parallel programming. Now, assuming you're familiar with C++ and you came across these married of parallel programming facilities, and this is a very partial list, of course, and they might look like a strange mix. But if you look closer, and this is what I'm going to talk about now, they are actually parts of different programming models. So what are these 4 programming models? The first one is kind of a non-model or unstructured, which I had to put in some bin. And it includes the most basic facilities that are mostly been provided in C++11, and that includes thread and mutex and the atomics and all those low-level and small-scale operations. The next model is task parallelism. It's used to include, or includes until for the upcoming year, mostly stood async, which was introduced in C++11, and starting from C++26, we'll have sender that will significantly extend and improve this model. Next, we have cooperative tasks or cooperative multitasking, which is based on coroutines. And lastly, we have data parallelism, which relies on parallel algorithms that were introduced on C++17. Now, these 4 models are not different abstractions levels. They're not built one on top of the other. They are completely different ways to structure your program. So in this talk, I'm going to go over each one of those different programming models, and then I'm going to talk a bit about mixing them. And this talk is about the force, namely the high-level programming models. It's not about the trees, which means that particular facilities that are covered or discussed briefly in the talk. So first model is what I call unstructured parallelism, which is basically an ad hoc use of the parallel facilities, which are built from the lowest level building blocks, provided mostly by C++11. It provides the minimal overhead, given you're using very low-level abstractions. And if done right, it allows the maximum utilization of the parallel hardware. On the flip side, as everything with C++, the lower you go, the riskier you are. They provide minimal safety, and so you must have the most expertise in order to use them correctly. So the major components of this model are first, at the lowest level, the memory model and related classes, such as atomics and friends, barriers and such, and thread local, which also represents the memory. And then we have higher level facilities, such as the ability to create a thread and the basic synchronization primitives, such as mutex, condition variable, and the ones introduced in C++20, such as semaphore and latch and barrier. And slightly above that, we have a few convenience utilities, such as all the RAII lock wrappers, call once, JThread, and so on. So the exclusive use cases for these kind of this model is mostly to construct higher level facilities. For example, you can create a thread pool, you can implement a spin lock using atomics, and so on. Creating concurrent data structure is also a typical use case. Instead of putting a big fat lock in front of a standard container, you can implement a certain data structure based on either locks that allow finer grain access, or even make it lock-free and provide a higher level of concurrency. And another typical use case would be allowing long-running services that are running in the background. Now, one thing that's missing in this model that relies on threads basically, is a way to communicate between threads. Okay. Basically, when you have a code that runs on a thread and it wants to communicate with another thread, then it has to do that through shared state. Okay, state that is external to those both threads and exist in shared memory. So one way to achieve this kind of synchronization is via atomics, which provide avoid data races. But atomics are very fine-grained, so you can communicate very small amounts of data using them. Another option, another possibility is to lock complete standard containers, but then the locking is very coarse-grained and you might eliminate the parallelism in your program. So having efficient concurrent data structures can solve this problem. There's nothing as of C++23. In C++26, we'll hopefully get RCU and hazard pointers, which provide building blocks for concurrent data structures, and concurrent queues are in the works. So a little bit about the pros and cons of this model. First, the obvious pro, we have a maximum amount of control. And if done right, we have a maximum amount of performance. On the flip side, we have a very complex memory model, and it's hard to make the ideal use of it. And it's obviously prone to data races and deadlocks and all those issues. Now, the thread abstraction represents a CPU or a processor, okay? It gets some entry point, a function, and it starts to execute it. But the thread itself has no functional semantics. There's no thread object that does this and thread object that does something else, okay? The thread is a facility. And this means that when a thread executes a certain function, and that function has to synchronize with some external state, then it has to include the function itself, has to include the synchronization facilities within its code. So instead of focusing on the functionality itself that the function provides, it has to also interleave synchronization operations. And this is possibly non-ideal. If we have a higher level of abstraction and more involved runtime, then we can do less work, we can have less bugs, and we can hopefully get better performance. And this leads us to the next programming model, which is task-based. And in this model, a task represents a limited amount of computation, which is mostly independent, and ideally gets some input, provides some output, but does not have any side effects. Namely, it does not change any external state of the program. Typical tasks would be functions or lambda expressions or loop iterations and so on. And the nice thing about tasks is that they can decouple the functionality from the execution. So we can have one thread that executes many tasks and one task that migrates among different threads. And the task itself doesn't have to worry about the execution context and the accesses to shared data, which is protected by the runtime. Now, tasks are inherently asynchronous. Otherwise, you can just run functions sequentially. They are designed to run somewhere, somehow, by the runtime that manages the tasks. And whoever created the task can ideally continue to do some useful work until that task completes. The way that caller accepts the output of the task is either via a future object, which we'll see in a minute, or if the model allows that and the runtime is efficient enough, it can chain the output of one task into the input of another. So the existing way of implementing tasks in C++ is using std_async. And what async gets is a lambda expression or a function, and it returns a future which represents the outcome of the task execution. After calling async, the task goes on and executes. The caller can continue to do whatever it wants, and then when it needs the results, it calls the get member of the future and obtains the results. Now, the execution of a task using std_async can have a few schedulings. One is, and they're determined by the when parameter that is given first. The first is using, if we specify launch async, then the task or the lambda or whatever is executed as if on a different thread. Okay, so whether it's on a newly spawned thread or on some pre-existing thread pool, that's like an implementation detail provided by the runtime. But it's not executed on the current thread, on the caller. Another option is deferred, which means the task is executed only once the result is asked for. So only once we call get. And if we don't call get, then the task isn't executed. And lastly, we can combine them with async and deferred. And in this case, it's up to the runtime to determine whether it wants to execute the task on a thread or on demand. So the limitations of std_async tasks are, first, there's no composition. You can't schedule one task immediately after the other or await multiple tasks and so on. This has been proposed in the past, but didn't come to fruition. There's no way to configure the execution. So you can't say, I want this task to run on this thread pool and another task to run on something else. It's all up to the runtime. There's no scheduling options. You can't stop an existing task that's being executed or yield for a while. And this is basically a frozen facility, no progress since C++11. With C++26, we get sender receivers, which offer a much richer model. They are composable, which means you can chain tasks and you can split tasks or change them into multiple other follow-ups, and you can await one or many tasks and so on. You can use any kind of scheduler you want, whether it's based on thread pools or coroutines or GPU or what have you. It has built-in support for stopping and for error reporting, and it's coming up soon. To get an understanding, if you somehow haven't seen a talk about sender receivers, this is a very simple use case for senders. So we define, first the auto tasks defines, or is a variable that will hold the graph of tasks, which will include first the just defines just a value. It doesn't execute anything, it just emits a value for the rest of the chain. And then the pipe and then moves the value emitted by the first task into the next task, which combines the world with the hello, and returns that from the second task. And this, the return string is automatically chained or piped into the third task, which prints it and returns nothing. So we have This creates like a chain of 3 tasks, but it doesn't execute it until now. It doesn't do anything. And when we call sync await, then the caller blocks and the task graph starts to execute until it completes, and then the caller can continue. So senders are the future of async C++. Okay, they are extendable. They allow many options. They provide flexible task graphs, as we've seen. Like the little graph I show here is actually possible using senders, but not using async. And in general, they are a common infrastructure for any async operations, not necessarily as part of a task-based model. So this brings us to the third model, which is cooperative multitasking. It is related to the previous model, which is also based on task, but it's slightly different. And we're talking now about tasks that are either a bit longer or can potentially block. Okay? And the use case we care about is having a number of tasks that is much larger than the number of cores. Because if we have like fewer tasks than cores, we have plenty of compute work. We don't care if a task blocks. So in this case, we want to be able to do something useful when a task is blocked. We want to be able to continue executing, doing useful work on the compute resources we have without stalling until the block task continued. Now, if, for example, we have a task that blocks on some mutex, okay, or some synchronous I/O operation, then if it were a threading-based execution model, we have a lot of threads, and the operating system manages those threads, okay, and one thread executes until it's blocked by I/O or by a lock or whatever. Then in this case, the operating system will move the blocked thread aside and schedule some other thread. So this is how the operating system handles thread scheduling. But we're now talking about task-based scheduling, and tasks are a user mode concept. They are not something that the kernel is aware of. So in this case, if a task gets blocked, then the kernel can't help us. It can, in general, deschedule the thread that's running the current task and run something else, but that something else, it might not be part of our program, and this is not what we want. We want to be able to utilize the compute resources that we have as much as we can. And this is where coroutines come in handy. So coroutines, introduced in C++20, are functions that can be explicitly suspended and resumed from within your own C++ code. This means there's no operating system involvement, there's no assembly required, there's full language support, well-defined state management, error handling, and so on. So for example, we define a simple coroutine which first prints something and then co-awaits. We'll discuss that in a minute. Thus, doing so suspends itself and returns the control to the caller. And once it's resumed, it prints something else, and so on. And the behavior of this coroutine is defined by the coro_t type, which is a complex type that's beyond the scope of this talk. But it defines a coroutine and the semantics of its suspensions and behavior. And when we call this coroutine from a main, then first we create the coroutine and start to execute it. It will go ahead and and print the before await. Then there's a call to co-await, or which suspends the coroutine and returns control to the caller. And then the caller prints whatever and resumes the coroutines, which returns control to the coroutine for the last print. And once the coroutine completes, the control is returned to the main function, to the caller. Now, the key element here is the co-await part. Okay, co-await takes an expression and evaluates it, and the evaluated expression should return an available object. And that available object is the scheduling point. Okay, it has three functions. First, the await ready, which indicates whether the coroutine can be suspended at all or should be suspended at all. Then await suspend, which actually actively suspends the coroutine and returns the coroutine handle. And finally, await resume, which is called after the coroutine is resumed. Now, when we call co-await foo, then first the foo function is executed, and it returns the awaitable, which determines whether the coroutine should be suspended or not. And this is the scheduling point, the point where we should determine whether the coroutine continues or is moved back and some other code is executed. So co-await by itself does not create any parallelism, okay? It just performs a user-level context switch between the current coroutine and some other coroutine or the caller. It is up to the program to track suspended coroutines, okay? Unless we have like one coroutine that you go back and forth, as I saw in this little example. But if you have a lot of coroutines that can be in a suspended state at the same time, then it's up to the runtime of the scheduler to track their suspension and to recognize when those suspended coroutines are ready for re-execution and to figure out when they can be executed and resumes their run. And what we need for a reasonable task-based runtime that is actually useful in a task-based execution that uses coroutine is first and foremost some sort of parallelism. Okay, if there's no parallelism, we have just a single core running everything, then we get nothing from task-based execution like this. It makes sense in other use cases of coroutines, such as generators, which are a different story and unrelated to this model. So we do need some sort of parallelism, and we need a scheduler. Now, just clarifying the point about having some sort of parallelism, if we have none, which means we have a single CPU, okay, processing everything, and we get two tasks, then they are both executed on the same processor. They can be interleaved, but that doesn't bias anything. In the end, the time it takes to execute is the sequential time of the both tasks execution. If we have multiple CPUs, then we can leverage many CPUs to run many tasks, and we get faster execution. And if we have some parallelism that relies on the I/O, we can also get parallelism. This means we can get I/O parallelism from the disk device, okay, which can process reads and writes in the background in an asynchronous way. And we can get parallelism when we perform a network call and have some other remote machine do the processing while we continue to do other stuff. So a simple example of how it would look like when we do coroutine-based multitasking. Say we have a coroutine task scheduler that starts to execute a certain task. At some point, that task invokes async I/O operation. Now, the fact that this is an async I/O is important. If that I/O isn't asynchronous, it's blocking, then the whole thread will block. And this is a problem, okay? Because then we can't schedule anything else because the whole thread is blocked. Our scheduler can't be executed. But if we start an async I/O operation, we don't want to just wait until it completes. We can tell the scheduler that we need to be descheduled. We can move back. And this is the cooperative scheduling part. The coroutine suspends itself, and then the scheduler can switch to another task, use that CPU. When the async I/O completes, then the scheduler has to be notified in some way that the operation started by this particular task has completed, and this is something that has to be implemented. The scheduler has to be aware of the I/O system, and vice versa. And the scheduler can then mark the task as ready for re-execution, and when possible, resume its execution. So when we built a coroutine-based scheduler, we commonly want to have one thread per core. There's no really need, or it doesn't make a lot of sense to have multiple threads per core. If we are going to manage, or our scheduler is going to manage the tasks on its own, then a single thread per core is the ideal way to go. This also means that suspended tasks can move among cores. If one is suspended on a single core, certain core, it can be resumed on another one. And this can provide a lot of fun events if that coroutine uses a thread local memory or grabs a lock in a single thread and tries to release it from another. And this means that any synchronization objects, in case there's a need, should not be the native operating system synchronization objects, such as mutex and so on. If you're going to use locking in a coroutine-based tasks environment, then you want to have coroutine-aware synchronization primitives. You want to have your own implemented coroutine lock that just suspends the coroutine instead of just blocking it and blocking the whole thread. Now, this all requires a pretty involved scheduler. Okay, it has to track the suspended tasks, the new tasks. It has to get signals from different places and so on. So the scheduler itself is not easy. It's going to be a complex, to include complex data structures, concurrent data structures. It's going to be implemented using the unstructured building blocks. But once that is done right, then the coroutine-based tasks are freed from worrying about all these implementation details. So one last thing about this distinction between threads and tasks. So threads are, as I said, parallelism abstraction. They represent a CPU, while tasks are mostly a concurrency abstraction. They represent a certain function or a piece of functionality that is pretty independent and can be executed as a whole in different places. Threads are suitable as background services, long-running things, worker threads, and so on, while tasks are usually supposed to be short and independent, and their number can be very, very large. Threads can be used to perform long-running, complex parallel operations, okay? While tasks are usually suitable for smaller scale, more local operations. And finally, when we do run a thread or a thread-based workload that does a lot of processing, we want to make sure that the amount of work that each thread gets is about the same to ensure load balancing. While in the task-based model, since we're talking about mostly small-scale, dynamically executed tasks, then we get load balancing pretty much for free. Now, one other concept that is related to both threads and tasks and coroutines is fibers, also known as user threads or green threads. And those are a slightly different beast. They are basically stackful coroutines, which means each coroutine has its own stack. Now, in conventional standard coroutines, each coroutine has a single stack frame, which is the coroutine state, and that's it. When the coroutine is suspended, its state is placed in that stack, and that's it. And this means that coroutines can only be suspended from within the coroutine function itself, but not from functions that the coroutine calls. Okay, and in the case of stackful coroutines or fibers, then that's not a problem. The fiber can be suspended from anywhere. Like any nested call, any level of nesting, it can suspend itself, and that's just fine because the whole stack moves aside, and the following fiber will use its own stack. And this actually allows fibers to be more of an execution, like a generic execution context, like threads. Okay, we said that threads can take a function, any function, and execute them, and it's separate. The behavior of the function is separate from the thread itself. And the same goes for fibers. Since fiber can be suspended at any point, it can also be like a generic execution context that can take any function. A fiber can take some function, start to execute it, and be suspended at any point. Now, similar to what I said about coroutine synchronization objects, such as mutexes, same goes for fibers. If you wanna use synchronizations with fiber, you don't want to use the operating system level synchronization object, but rather dedicated custom-made synchronization objects that are tailored for those fibers and can inform the scheduler that the fibers has been suspended. Fibers are not supported in C++. I have no idea if there's a plan or not. But they are, I can say that they are heavily used, or at least somewhat used in the real world. So this brings me to the final model, which is the data parallelism model. And in this model, the parallelism stems from the data itself. We're talking about massive processing of large amounts of data, which is mostly independent. Like the data elements are mostly independent. And the processing operations are ideally fairly small and simple. So the parallel algorithms introduced in C++17 have in general the following form. We have an algorithm which is called from some caller sequentially. Okay, the invocation of the algorithm is a sequential operation. We then have an execution policy which defines what kind of parallelism behavior we allow. Okay, and this dictates what the runtime is going to do. And finally, we have the container, which determines what's the data whose processing we actually want to accelerate. So this is a high-level abstraction, okay? It doesn't give us a lot of control. We can say what are the safety semantics that we require, but we can't say much more than that. Other than that, we don't have any control over the amount of parallelism, the thread pool that will be used, how load will be balanced, and so on. This is up to the runtime. But since we don't have a lot to say, then the runtime has a lot of freedom, given our when we specify our requirements, then the runtime has a lot of room to optimize the execution. And when this is done properly, then we get no data races, no deadlocks, and we can utilize very parallel machines or even CPUs or GPUs. So let's see some examples. Here we have this container that holds a massive amount of data, which we want to execute in parallel. We want to sum all the numbers. So we call a reduce operation and give it a execution policy, which we'll see soon what kind of policies we can get. And then what's executed is a parallel algorithms or not. It's up to the runtime to determine whether it's reasonable to parallelize this kind of massive processing or not. If it does run things in parallel, then the complexity of the parallel algorithm can be more, it can have a slightly higher complexity than a sequential algorithm because parallelization sometimes requires that. And the actual implementation isn't defined. It's only the semantics of the synchronization, okay? A certain implementation, as I said, can execute a parallel algorithm on the GPU and so on. Now, we have in the language 4 policies. The first one is sequenced, which means the parallel algorithm is going to be executed on the current thread and only on the current thread, which means it's not going to be a parallel execution. It has some minor differences from a non-parallel algorithm without this policy. And lastly, the policy parameter is a type on its own, okay? And this means that each policy has a different type, and this means that the behavior is determined at runtime. Okay, this isn't just a value that can be determined at runtime. So we have to determine the parallelization we are good with at compile time, which makes sense. The second policy is a parallel policy, and in this case, the parallel algorithm can utilize multiple threads, and per thread, it's like it's being executed sequentially. Okay, like every thread executes a single operation at a time. It does not execute multiple operations at the same time, interleaving between them. And now if we put some lambda expression that does some nasty stuff, we can cause data races. That's possible, but we should ideally not do that. The next policy is parallel unsequenced policy, which differs from the previous one by allowing a single thread to process multiple data elements at the same time, namely interleave processing of multiple elements. And this allows, in practice, the use of SIMD operation and vectorization. And lastly, we have C++20 edition, which is the unsequenced policy, which means the execution is going to be on a single thread again, but now there's no requirement that it doesn't execute multiple operations in an interleaved way. So it executes on a single thread, but it can use SIMD operations to speed up the execution. And in addition to those 4 standard policies, vendors can provide additional ones that can let you execute the parallel algorithms on different kind of processors, GPU, FPGA, or what have you. Now, parallel algorithms does not mean parallel containers, okay? In C++, algorithms and containers are a different thing. And we can't have containers be thread safe by default because that has an overhead. And this means that if we execute just regular sequential parallel algorithms, then we will pay a price for something we didn't ask for. So parallel algorithms can generally modify the data itself in their target container, but they can't modify its structure because that would be a non-safe operation. And if we run some parallel algorithm on a certain container, then the algorithm guarantees that there are no data races, but if our own program accesses that container from another thread, then we might cause a data race, and that's our problem. So the last thing I want to talk about is mixing models, okay? We discussed 4 different models. What happens, or how can we, and when should we mix and match? So first thing is, when our program mostly uses unstructured parallelism, which means the basic building blocks we describe. It has some custom use case for it, or custom utilization, maybe a server that uses some worker threads, and so on. If our program utilizes most of the cores, then we don't have a lot of room for additional parallelism. So we can use coroutines for async I/O, but other than that, not much else to do. We don't want to invoke or create more parallelism because we don't have the capacity for that. On the other side, if most of the cores aren't used, our program has some parallelism only for, say, some background processing services or whatever, then we have enough resources to do other kinds of parallelism, use tasks or parallel algorithms. The impact of that is, it depends. Because the runtime that provides the parallel execution for task-based executions and for parallel algorithms is unaware or potentially unaware of the threads we have created on our own. And of course, in this case, we have to be careful with shared state. That I mentioned. So next use case is when we are using task-based parallelism, either based on async or sender-receivers. And again, we're talking about the case where most of the cores are being used. And in this case, again, we don't have a lot of additional resources for additional parallelism. There's no point in creating new threads or using parallel algorithms. We won't have the compute resources. If we're using some task-based model, using coroutines for additional operations, it's kind of awkward. Maybe it makes sense in some case, maybe it doesn't, but it would be best to just use the existing task-based system in this case. Now, if most of our cores aren't being used, we only use a task for certain async operations, UI work or whatever. Again, we can use parallel algorithms, assuming we have enough compute resources. from within a task to accelerate some computation. Creating a thread doesn't make much sense because tasks are short-lived. And we have to be careful with using synchronization mechanisms such as mutexes, as said, because they might block the task. The next case is when we have a coroutine-based execution. And in this case, if most of the cores are used, so we have a scheduler that runs threads, multiple threads, and schedules tasks that are based on coroutines. And this point, in this case, I really see no reason to use any other forms of parallelism. And if most cores aren't being used, say we are only using those tasks to run some I/O operation, then again we can use parallel algorithms, but it will block the coroutines, and that's like a nasty situation. Similarly, using async or sender-receivers tasks, assuming they are run within the context of another task, it doesn't make much sense. And again, tasks are usually too short to creating new threads. So not a lot of options there. And lastly, if most of our parallelism relies on parallel algorithms, then we can maybe do more work using the lambdas that take place in the parallel processing, but that would be really awkward to use any kind of any other model. No point in spawning async tasks while we're using the parallel threads. It would be a wrong place to use coroutines, and we certainly don't want to use any synchronization mechanisms as much as we can avoid that, like blocking on mutexes and so on, because that will kill the parallelism of the parallel algorithm. So in summary, we've discussed or we covered 4 different parallel models. The first is the unstructured one, which is based mostly on the C++11 low-level building blocks. The second is the task parallelism, which achieves or provides functional decomposition of the program we want to parallelize. It used to rely on stud async, and now it will be much better with senders and receivers. The next one is cooperative multitasking, which relies on user-level scheduling based on coroutines, which is great for for handling with async operations, but the standard does not provide a scheduler for this model. And lastly, data parallelism, which is designed to accelerate the processing of large amounts of data in a mostly uniform way. This is a declarative API. It's very safe and can be very efficient, but we don't have a lot of control over the resources it's going to use. And as we've seen, mixing model hardly works, and that's because parallel programming is hard. With that, I'm done. I'm happy to take any questions.
The project that I work on does parallelism with a lot of processes rather than threads. What can I do to convince them that it's worth moving on to threads?
Oh, I'm guessing you have a very good reason to use processes instead of threads. I mean,
It was made 25 years ago.
Then I think I mean it's a different language. It's I think it makes sense to move on because 25 years ago C++ didn't support threads. We didn't have all these convenient facilities. Using processes is like the communication is non-standard. I think there are too many reasons to move to a more standard implementation other than the fact that you probably have to invest in that.
Hi, thanks for the great talk. My question is, I have an application which has a blocking I/O thread. Is there any way to have some parallelism in that scenario?
Well,
or I have to have the thread keep on blocking?
Yeah, if the I/O is blocking, then you want a thread-based parallelism, because then the operating system is aware of the fact that your current thread is blocked on the I/O, and it can deschedule it and schedule something else. So that's a use case for parallelism that's based on threads. In many cases, you can just switch to async I/O, use an async API, and then you can switch to one of the other APIs, one of the other models.
So there will be always a blocking scenario, right? I mean, even with CPU, the OS coming back, it would still be, we will still block on the thread. The CPU is still going to keep on blocking, right?
If you're using the blocking. Yeah.
There's nothing.
But in this case, the operating system knows that your thread is blocking on some I/O operation. So it will move the thread aside and have some other thread run instead of it.
And then it would be like polling for the thread to complete the operation, or how would it know?
It's the operating system scheduler. It's aware of the I/O operations.
Oh, okay. All right, thanks.
Thank you. The task parallelism async, you said you can't compose them, right, to make the graph.
Yeah.
But can you just pass the futures in to like nest them?
So in your own code, you can start an async operation, then wait for the future, and then start another async operation. But the control will have to go back to your function, and then again, and so on. It doesn't flow automatically. So it's kind of building your own infrastructure or your own chaining.
It's a little messy.
And that's less efficient and more cumbersome, more work than a model that provides this kind of chaining and graph creation in a built-in way, like Senders.
Thank you.
Okay, so thanks all for being here.